Hey, all you cool cats and kittens. In this video, we are going to learn about the properties of logarithms. Honestly, I can't think of a cooler lesson than the properties of logs. Everybody loves logarithms, right? Yeah, crickets usually. All right, listen, it's actually not that bad. I hope you guys already learned about logarithms, but the first question maybe you're asking yourself right now is, what's a logarithm again? So let's talk about that first. So logarithm is literally an exponent, right? Everybody knows that the inverse of addition is subtraction, the inverse of multiplication division, the inverse of a square is a square root. Well, the inverse of an exponent is a logarithm. So literally they are inverse operations for an exponent. So think of it like this, a log equals an exponent. So the basic rule is this. Let's start at the bottom here. If you have a base b raised to the y equals x, that's exponential. This is exponential because the variable is in the exponent. So what we could do is we could solve for that exponent by using a log. So log base b, so your base is always the same, of x equals the exponent y. Now that still may be a little bit tricky, so let me do an actual example that might make a little bit more sense. If I have 3 to the x equals 97, and I said, hey, what's x? Well, I don't know. I know 3 squared is 9, so it's not 2. I know 3 to the third is 27, so it's not 3. I don't know what x is. That's weird. I don't know. 3 raised to what is 97? I have no idea. Well, we could actually solve for x by using a log. So all we got to do is use the log definition, which is log base 3 of 97 equals the exponent. So again, the exponent is what you equal when you're using a log. The base is the same base, in this case 3, and they have 97. So if you use your calculator, which most of you I bet know how to do, but I could show that in class if we need to, is that log base 3 of 97 is x. So just in case you're wondering what the actual value is, if you use your calculator, it's about 4.16. Now, it is an irrational number, so it's approximately 4.16. You know how much I hate approximations, so I'd much rather you give the exact value, log base 3 of 97. So 3 raised to about 4.16 will get you really close to 97. All right, so that's the idea of a log. All right, so let's talk about the base real quick. Now, the base could literally be any value, any positive value, but there are two very common bases. That's base 10 and base e. So if we have base 10, we really just save our time and write log. If there's no base written right here, it's assumed or implied that it's base 10. If I want log base 2, I got to put a 2. If I want base 5, I got to put a 5. But if I don't put anything there, it's assumed that it's base 10. So on your calculator, kind of next to the 7 on your calculator is a log button. That is log base 10. Then we also have log base e, which you could write like this, log base e. But in the math world, we abbreviate that and we just call that ln. We don't put a little base here. Again, it's implied that it's e. Now, if you're like, what is e? Well, e is, it's an irrational number. It's kind of like pi, right? It's just a lesser known one, but it's an irrational number. It's used a lot in the financial world, and we'll talk a little bit more about application stuff later. But it's just a number. It's an irrational number. It's not a nice, solid, whole number. But it's called the natural log. Anytime you're working with base e, it's called the natural log. So that's why we use ln, the log of the natural. I would have went with nl, natural log, but whatever, semantics. So anytime you see an ln like this, it's implied that we are working with a log that has base e. And if you really want to write this, it's fine, totally fine. But we usually shorten it to ln, the natural base. All right. So, but again, a log can have a base of any positive number that we want. Okay, those are just two common ones. All right, so let's talk about the 4 huge properties of logs, and I actually have them repeated because on the left side I have just a random log of any base. We're just calling it a, any base. And then on the right-hand side, I specifically use the natural log ln, which is base e. Okay, but again, these rules work for any base. All right, the first rule is that if you have log of any base of 1, the answer is always 0. And the rationale as to why that is because a, any number raised to 0 is always 1. That's what's true, right? So if I said, hey, log base 5 of 1, you'd say, 0. Log base 22 of 1, well, you would say 0 because, again, 22 to the 0 is 1, 5 to the 0 is 1, any number raised to the 0 is 1. So that's a simple property. All right, log base a of a always equals 1. If your base and what you're taking the log of match up, well, then your answer is always going to be 1. So log base 5 of 5, 1. Log base 26 of 26 is 1. What's the rationale as to why? Because any base raised to 1 is always itself. Any number raised to itself is equal to, any number raised to 1 is equal to itself. So that's why if the base and the value that you're taking the log of match up, answer is always 1. And look, if we come over here, these same rules are true even with the natural log. Remember, natural log is a base e. So we just don't write the base there because it's implied. But when the base matches up, e and e, always get 1. All right, here's another nice rule. And it is that if you have log base a of a to the x, which means you have an exponent in your log, well, then you just equal that exponent, okay? So if you have log base 5 of 5 to the x, you just equal x. But again, your base they have to match up. If you have log base 5 of 6 to the x, well, that's not going to be just x anymore, right? The bases have to match up. And the last rule or property is a pretty important one. It's actually really, really common sense. It says if you have log base a of x equals log base a of y, well, it implies that x and y are also equal. But again, your bases have to be the same. So if I have log base 5 of x and I equal log base 5 of 17, well, then it implies that x must equal 17 because the two bases are the same. Well, then what you're taking the log of must also be the same. So it's, it'd be like this, right? If I said 5 times 2 equals 5 times x, what's x? 2, because 5 times 2 is equal to 5 times 2. So the only thing that x could be is 2. So it's kind of similar to that idea, but with logs. All right, so those are the main properties of logs. We actually have a couple more though, but those are like the 4 basic ones. All right, so here's a continuation. So here are 3 more properties of logs. These properties actually have specific names: the product property, the quotient property, and the power property. I know you've seen these before. I know you learned these, but we just got to really quickly review them. So the product property says if you are multiplying 2 values inside of a log, again, multiplication is happening inside the log. You could split that up with 2 logs, log base a of u plus log base a of v. So the multiplication splits up with addition, but you got to produce 2 logs. And this is the same if it's natural logs, right? As long as you have multiplication of 2 values inside of a log, even if it's natural log, it splits up to natural log of the first plus natural log of the second. So again, it splits it up with addition when you have multiplication inside, okay? These rules do go in reverse. So you could also say if I'm adding 2 logs, then I could combine that to log of multiplying them. Okay, but I have to say this, like a little kind of, note here. If I have addition inside of a log, that doesn't do anything. You can't do anything with that. You can't break that apart because none of these rules talk about addition inside of a log. There's multiplication inside of a log, and that splits apart into addition of 2 logs. But there's no rule for adding inside of a log, so please don't accidentally think that. Okay. The second rule is the quotient property. It says if you are dividing 2 values inside of a log, so log base a, u divided by v, you could split that up with subtraction. So it's log of the denominator, log of the numerator minus log of the denominator. The denominator has to go after the minus sign. And again, same thing with natural log of u divided by v. I'm dividing, so I could separate that with subtraction. Log u, natural log of u minus natural log of v. All right, so again, quotient property, if there's a quotient division inside of a log, it could separate with subtraction. Now the power property says if you have a power inside your log, if you have a power, in this case it's n, you can actually pull that power in front of the log, like as a coefficient, and they are equal. So again, let me kind of give you an example of that. So if I have log base 2 of x to the 4th, that is equal to 4 times log base 2 of x. So that power is allowed to drop down in front. Or you could go in reverse. You could take that 4 and move it back up if you so desire. So again, all of these properties work in two ways. You could go left to right or right to left. You could take addition of two logs and combine it to multiplication inside. You could take subtraction of two logs and combine it to division inside, or you can move around that power. But note, your bases always have to be the same. You can't have 5 or 6 or even 2 different bases. Your bases have to be the same, whether it be 2, 3, 4, they gotta be consistent, okay? So the key thing is, what do we do with these properties? Well, we actually use the word expand or condense. So if I'm going from one log to multiple logs, we call that expanding. If I go from multiple logs to one log, we call that condensing. So a lot of the times we're working with expanding and condensing. And this is going to be like, why are we doing this? Well, it helps a lot when we have a later video about solving logarithmic equations. Okay, so let's just briefly pause. I want to make sure that you understand where these rules come from and why they actually do work, why they're true, because they're very weird rules. Like, how could you go from multiplication to addition? How's that work? Well, let's prove it so you can actually understand it real quick. So the first thing you have to do is let each log equal a value. So I just went with x and y. It was just simple. I could have used m and w or m and p or q and t. It doesn't matter. So I'm letting x equal log base a of u, and I'm letting y equal log base a of v. So the first thing I could do is understand the definition. Remember, the definition says a to the x equals u. A to the y equals v. And real quick, a side note, I'm using u's and v's, but be very careful that v's have sharp at the bottom and u's have a curve at the bottom. You don't want to mix up a u and a v. Maybe they were a bad choice, but anyway, I digress. All right, so again, I just used the definition. Remember, right? Logs equal the exponent. So x is the exponent. A is the base. U is what I equal. Here, a is the base. Y is the exponent. And again, v is what I equal. So if I think of it like this, right? What is u times v? Well, if I take u, which is a to the x, and I take v, which is a to the y, okay? Then what we could do is we could use a property of exponents that I really hope you know, and that's if you multiply exponents with the same base, you could add the exponents together. So that's kind of where we think about multiplication changing to addition, right? It's not that multiplication and addition are equal. Obviously, we know they're not, but it's about this idea of it's an exponent rule that if you're multiplying two exponents that have the same base, a to the x, a to the y, you're allowed to add the exponents, x plus y. So again, I'm just following rules that I already know. Now what I'm going to do is I'm going to reverse use the definition, right? Check this out, the definition, right? Now I'm going to look at this statement right here, and I'm going to use the definition of a log. So it says log base a of u times v equals the exponent x plus y. Okay, so let's walk through this one more time. So the first thing I did was I just said, hey, let's just call log base a of u, let's just call it x. And let's call log base a of v, let's call it y. Then I used the definition of what a log is to write it as an exponential. A to the x equals u, a to the y equals v. Then I said, all right, well, what's u times v? Well, that'd be a to the x times a to the y. I'm allowed to add the exponents to get one base, a to the x plus y. Then I reverse use the definition of a log, which says that a log of u times v, base a, equals the exponent x plus y. And then I can finish this off by saying, but wait a minute. Isn't x log base a of u? Yeah, that's what I said it was. Plus, isn't y log base a of v? Yeah, it is. That's what I said it was. And there we go. There's the definition. Log base a of u times v, multiplication inside of a log, is equal to the addition of the two separate logs. Log of u plus log v. All right, so hopefully you followed that. Maybe you got to watch that 2 or 3 times to follow exactly what I did there. But I just utilized properties and rules that I know to get the statement that I wanted to get at the end. All right, so let's actually use these properties. All right, we talked about expanding or condensing. So expanding means taking a single logarithm and creating more logs, which could be a good thing or bad thing. And condensing means taking an expression with multiple logs and simplifying it to a single logarithm. So again, why do we do this? It's going to come in handy later on when we talk about modeling. It's also going to come in handy when we talk about solving both exponential and logarithmic equations. We need to be able to do this because it's going to make our lives easier later on. All right, so let's look at two kind of simple examples here with some numbers, right? All right, so write each logarithm in terms of natural log of 2 and natural log of 3. All right, so here's my thought process. The natural log, I could rewrite 6. 6 is 2 times 3. And then what I could do is I could use the multiplication of the product property to expand that. That's natural log of 2 plus natural log of 3. So I was able to go from natural log of 6, and I was able to change it to an expression. I expanded it to the natural log of 2 plus natural log of 3, just using some basic ideas. This next one's slightly trickier, but I think you'll catch on. So on top, I already have a 2. But 27, I like 2s and I like 3s, right? I want to write this in terms of 2s and 3s. 27, 27 is 3 cubed. 3 times 3 times 3 is 27. So now what I could do is I could do two properties. First property I'm going to use is the quotient property. Natural log of 2 minus natural log of 3 cubed, because division breaks apart into subtraction. Then I could use the power rule and drop down this power. Minus 3 natural log of 3. So natural log of 2 minus 3 times natural log of 3 is a expanded way of expressing the natural log of 2 over 27. I'm just using the rules. Hopefully that makes sense. All right, let's do a couple more examples here. This time we're going to look at some examples that have some variables involved in them. Okay, so I want to expand. So notice each of these statements has a single log. Here I have a log base 4. Here I have a natural log. And I want to expand, meaning I want to write this with multiple logs. All right, so I got a lot of multiplication going here. I got 5 multiplied by x cubed multiplied by y. So multiplication can expand with addition. So I got log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. Once again, multiplication expands with addition. So I'm going to use one more product, or the power rule. I'm going to bring down this 3 in front. So final answer, log base 4 of 5 plus 3 log base 4 of x plus log base 4 of y. Now, if you ask me, that's more complicated, but as we'll learn in the future, sometimes making it more complicated is actually helpful. All right, let's try this next one. This next one's a little bit trickier. It can mess some kids up, so let's take our time. All right, on top I have 3x minus 5 in a square root all divided by 7. So the first thing that pops in my mind is the quotient rule. Division I could separate with subtraction. So I have the natural log of the numerator minus the natural log of the denominator. Okay. Now the next thing I want to point out is inside of this log is subtraction. We don't have any rules. In fact, there aren't any rules that tell us that we can break apart subtraction inside of a log. Let's just quickly go back to the rules real quick. I just want to make sure everybody understands this, right? The rules are if you have multiplication or division inside a log, then you can expand. There is no rules for addition or subtraction, so I'm sorry I can't do anything, but I can do one little thing here. We know that a square root is equivalent, or you should know, to a 1/2 power. If you didn't know that, look it up. You better. All right, so what I can do is I could rewrite the square root as 3x minus 5 to the 1/2. Then I could use the power rule and actually drop that 1/2 down. But I have to emphasize one more time, I cannot do anything with the inside. It's done. Do not try to break that apart. Some kids will say, oh, but isn't 3 times x natural log 3 plus natural log of x? Yes and no, but if that minus 5 was not there, then yes, you could break apart the 3 times x by natural log 3 plus natural log x, but the minus 5 is there, which is it's not just 3x, it's 3 times x minus 5, and the moment you have that other operation of subtraction there, sorry, you can't do that. So do not try to reduce or break that apart. It just is going to have to stay exactly like that. All right. Let's try another one here. You can even pause and try this one on your own if you want, and then just quickly look back to see the answer, or fast forward to see the answer. This one's actually pretty easy. So I have log of several multiplications here. So I have log base 10. You don't have to write the 10, obviously. Log of 8 plus log of x. And you know what? You guys are pretty smart. You could probably do see ahead of time, ooh, that's a power that I could pull down in front of the log of y. And now I'm done. Easy. All right, let's try another one here. Again, some of the one we saw earlier. So I'm going to first break apart the division with subtraction. So natural log of square root of x squared plus 5 minus natural log of x. Then I'm going to realize, oh, a square root's really a 1/2 power. So that's going to be x squared plus 5, forgot the square, to the 1/2 minus natural log of x. Then the 1/2 could drop down in front. And that's really about as far as I can get. So a couple more little things, right? Oh, a lot of kids say, oh, can I move this power of 2 down? No, no, no. Remember, there's a plus 5 in there. The moment you put a plus or a minus inside of a natural log or any other log, you can't do anything. There's no rules that allow you to expand or condense with an addition inside of the log or natural log. So unfortunately, no, you cannot bring that 2 down in front. So the final answer is right here. Now again, here the 1/2 was on the outside. So that's why I was able to bring it down in front. All right, let's talk about condensing now. So here's an example where I see 2 logs. And I'm like, I don't want 2 logs, I want 1 log. Okay, so now we could use the rules in reverse to get to 2 logs, or from 2 logs to 1 log. So the first thing I do here is I see this 2 in front, and I could use the product, or the, excuse me, I keep saying that wrong, the power property in reverse. I can actually bring that up here. So that's log base 4 of x plus 2 squared minus log base 4 of x. Then I can say, well, wait a minute, subtraction of 2 logs can condense to division. So that's log base 4 of x plus 2 squared, all divided by x. And there's my final answer. Okay? Nice and simple. So I went from 2 logs to 1 log. I had subtraction, brought it with division, and then I used the power rule to bring that 2 up. All right, another example. Right away, I see subtraction, so I know I'm going to use division. But hold on a second. I got to bring this 2 up first. Remember that you can use the power rule in reverse. So that's natural log of x to the 5th minus natural log of xy squared. Okay? And then I could say, all right, well, that's just, division, because subtraction can condense to division. So that's going to be x to the 5th divided by xy squared. Now, that's not a bad answer, but it's actually reducible. I can clean that up, and here's why. X to the 5th on top is pretty easy, but on the bottom, x times y squared is xy times xy. Then you got to do some dirty work, right? Xy times xy, that's xy squared, which would result in x squared times y squared. So then what I could do is I could actually clean up that x. X to the 5th, x squared, that's going to be x cubed on top over y squared on the bottom. So there's a nice final answer. And if you don't understand how I did that, well, then again, go back to algebra 2 for a second. X to the 5th on top, x squared on the bottom. You could subtract 5 minus 2 is 3. That's where I got the x cubed from. Or you could think there's 5 x's on top, 2 x's on the bottom, 2 on the bottom, cancel with 2 on the top, leaving me 3 behind. However you get there, just make sure you get to the end. So make sure you understand what I did there. All right, here's definitely a trickier one. So let's walk through this one for sure. This is the last problem, and I gave you a doozy at the end here, but we can figure it out. All right. The first is, the brackets are like parentheses. And if I'm following order of operations, start within those parentheses. So I can't bring the 1/3 up because it's not technically on a log. It's actually in front of the 2 logs. So just kind of leave it there for 1 second. Just leave the 1/3 log there for 1 second, or the 1/3 there. Now I have addition. I could bring addition together with, hopefully you're hearing, multiplication. So that's log base 2 of x times x plus 1. Okay? So I was able to, again, reverse use the addition property, taking the addition of 2 logs and bringing it together as 1 log, multiplying them together. Now, well, I guess I could do this real quick, right? I'm always looking to kind of clean things up. So I could multiply that out and get x squared plus x. I mean, I really didn't have to do that, but it does make it look a little nicer. And then now I could use the power rule and bring this 1/3 up here. So I got log base 2 of x squared plus x raised to the 1/3. Again, it goes on the outside. X squared plus x is a quantity. It raises up outside of that. And that's a great answer. Listen, I want to give you full credit for that. But there's one more thing you could do. I hope you know that 1/2 is a square root. Well, 1/3 is a cubed root. So I could even make this look even nicer by saying log base 2 of cube root of x squared plus x. And now I got a nice final answer. Please, you got that addition. Remember, for maybe the 15th time, there is no rule, there's no property for breaking apart addition inside of a single log. I could take a log plus a log, combine that, but if there's addition inside of a log, you can't do anything. So it's just kind of stuck like that. All right, guys, so those are the basic rules and kind of properties of logs. I know that they get a little bit confusing at times. I'm going to try not to give you the most complicated problems ever, but hopefully you understand where I'm kind of getting some of these rules from. Hopefully you're hearing this again. I'm assuming you learned this in Algebra 2, so it shouldn't be brand new to you. Just take your time, be careful, and my other recommendation is don't try to overdo the problems and then you end up making a mistake. Just use the rules as simple as they are, as basic as they are, and be very, very careful. I will say that there's one kind of thing I want to point out here, and just use a different color. A lot of times students will do this. Let's say there's a 2 in front of a log and they have an x plus 3 inside, right? That 2, using the power rule, comes out in top of all of it. Some kids will put it on the x and put it on the 3 and say x squared plus 9. Please do not do that. It's x plus 3 all squared. That square goes to everything that was in that log. Now, I like this answer, but if you wanted to, you could do x plus 3 times x plus 3. That's x plus 3 squared, which is x squared plus 6x plus 9. I mean, you could do that if you really, 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 really wanted to. I mean, I would accept that as a full answer. But some kids just rush in. They put on the 2, they put on the 3, they say x squared, they say 9. No, you're actually forgetting about the 6x. It's x plus 3 quantity squared. It goes on the entire thing, which is x plus 3 times x plus 3. So just be careful. I do see that mistake happen a lot. All right, guys. Love you. Hopefully it was a quick refresher on your log rules.